Assalamu alaikum. Up till now, we have studied about magnets, current, electromagnets, methods of magnetization and demagnetization, and uses of electromagnet. And in the uses of electromagnet, we studied about electric bell, magnetic relay, and circuit breaker. Now we are going to study the relationship between the force and the force which acts on a moving charge when the charge is in magnetic field. Okay, what happens when a conductor through which current is flowing is placed in magnetic field? So these conductors through which the current is flowing and they are in the magnetic field, they experience force, and moving charges also experience force. Okay, so stationary charge in a magnetic field will not experience force. For the charge to experience force in magnetic field, it has to be moving, and in order to experience maximum force, it has to move perpendicularly to the field lines. Or if it is moving parallel to the field line, then it will not experience force. Okay, perpendicular or any other angle between 0 and between like more than 0, because 0 means parallel, so no force, or 180 means anti-parallel, also no force. So in order to experience force, charge should enter at an angle. Okay, if this angle is 90 degree, that is the direction of motion of charge is perpendicular to the field lines, it will experience force. Let us now have a look at the specification of this topic which is required here, and because this topic leads us to study about the DC motor. Okay, because a conductor carrying current placed in a magnetic field experiences a force. So these are the specification. You have to understand that there is a force on moving charge particle when it moves in a magnetic field, as long as its motion is not parallel or anti-parallel to the field. You will understand at the end of this topic that the force is exerted on a current carrying wire in magnetic field. How to find out the direction of force? We will study about the Fleming's left hand rule, which will help us to find out the direction of force experienced by conductor carrying current placed in a magnetic field. And the applications are here of this effect are DC motor, loudspeaker, galvanometer. Okay, these all are the effect of applications of this motor effect. Okay, so this Fleming's left hand rule, it is actually a useful tool to find out the direction, which will be in direction in which force acts on the wire or on a moving charge. And in this case, we will take the direction of conventional current. Current direction is taken as direction of conventional current. Okay, and in the same way, direction of motion of positive charge is to be considered. The charge deflection by magnetic field. This is the magnetic field between north and south pole, two opposite poles facing each other. So field lines originate from north and terminate at south pole. If a charged particle enters perpendicularly, suppose we consider a positive charge. So this will deflect upwards. Okay, provided it is not moving parallel to the field lines. What does it mean? That is, it is going in the same direction as that of the field, means from north to south. Then charged particle will not experience any force. In the same way, if it is moving opposite to the field lines, that is from south to north, it will not experience force. Okay, if it is stationary, it will not experience force. Okay, it has to move at an angle, and if the angle is 90 degree, like here it is entering perpendicularly, so it experiences maximum force. And this is the direction in which a positive charge will be deflected. And if the negative charge enters, the direction of deflection will be opposite. Okay, so the positive charge, the direction is found by Fleming's left hand rule, and the negative charge, if it is negative charge, we will apply it for positive, and then we will mark the direction opposite for the negative charge. Now, like moving charge experiences force. So current carrying conductor, what is current? Current is a rate of flow of charge. It means in a conductor the charges are in motion. It means and the current carrying conductor, it has also field around it. Okay, so this field is circular. So this circular field, it uh, is in the other field. Okay, so it means the two fields interact. The field due to wire through which the current is flowing is circular, and if the wire is placed in the magnetic field, which is a uniform magnetic field between the two opposite poles, like this is a uniform field. How do you say this is uniform field? The field lines are parallel to each other and equally spaced. Okay, so if a wire is placed here through which the current is flowing, it will experience force. So if you apply Fleming's left hand rule, we will see it here in the other slide. That is, we have to stretch out your fingers in such a way that they are perpendicular to each other. So we will see that in the next slide, but let us see in which direction this wire is experiencing force. It is experiencing force in the upward direction. Okay, when we take the direction of current from positive to negative, it means if the direction of current is from negative to positive, okay, this is deflected upwards. So if the direction of current is from this side, like current was flowing from left to right, now it is flowing from right to left. So what will happen is the direction of current is reversed, the force will be downwards. Okay, direction of current is from left to right, the force is upwards. Okay, in the same way, if you reverse the polarity, the direction of force will change. If the direction of current is kept same, but you place south here and north here, means field lines will be towards us, okay, out of the screen of this laptop. Okay, so the field direction will be opposite and the current direction is same as is shown. The force will be in the downward direction if the polarity is reversed. Okay, and you can increase the amount of force by increasing the strength of the magnet and having greater current in the wire, and the direction of force is reversed if either the direction of current or the direction of magnetic field is reversed. Okay, and you can maximize the force by keeping an angle 90 degree between current and the field. Okay, so these factors will cause the field force acting on the conductor to be maximum. Here we have Fleming's left hand rule. See, the three fingers are stretched out, thumb, first finger and second finger. First finger represents field, second finger represents current, and the thumb shows the direction of force which a wire through which current is flowing will experience. So let us go back and see this thing. We apply this Fleming's left hand rule. So stretch out your uh, fingers of left hand in such a way that your first finger is towards the laptop screen. Okay, that is from north to south. So you don't have to keep it tilted. Okay, because this figure is shown so to give you the 3D effect, right? So just keep your finger pointing towards the laptop screen. Which finger? First finger, because that finger shows the field, and the second finger will point out in the direction of current. Okay, it will be stretching out in the direction of current, so thumb automatically points upwards, so it means this wire will move upwards. Okay, and if the current is in the opposite direction, keeping the field same, so you have to twist your hand this way, so that the current direction is now from right to left, keeping first finger pointing in the same direction. Just twist your hand by 180 degree, so that your direction of your second finger is towards the left side now. So your thumb now points out in the downward direction. So force will be in downward direction. Wire will be catapulted. It will be pushed. If it is free to move, wire will be pushed upward or downward depending on the direction of current and direction of field. So again the rule is shown here. So and the fingers are to be stretched out in the same manner as is shown in the figure here. Okay, so you cannot alter the fingers angle. Okay, just stretch out this way, keep your hand exactly in the same manner as is shown, and then you can only twist your wrist. Okay, so that you can find out the exact direction of force, correct direction of force, which acts on a wire through which current is flowing for different orientations, for different arrangement. Okay, magnetic field north to south, and current direction plus to minus means conventional current. Now here there are some informations which are missing. You have to fill it up. Here cross between the two opposite poles. So what is the direction of force? Cross here shows the current inside, okay, towards the laptop screen. So you have to orient your hand in such a way that your first finger goes from north to south, points towards right side. Twist your first stretch out the fingers like it was shown for the Fleming's left hand rule. Now you have to do the twisting of your wrist. So first finger goes from north to south, and second finger towards the laptop screen. So your thumb goes downwards. Okay, so it means the wire will experience force in the downward direction. So your orientation should be correct. If you have done this successfully, means the back side of your hand will be towards your face and palm of your hand will be facing your laptop screen. So force is downwards. Now here force is shown, and the field is also known to us, that is in the opposite direction to that of the first question, that is from north to south. So it means your first finger should point from towards the left side. Okay, and second finger downwards, thumb downwards. So when thumb is downwards, twisting it is a bit difficult, but you have to practice it. So the thumb now comes automatically downwards here. So your second finger will be outward. So dot. Okay, it shows the direction of current. Now here force and current are given. Which one is north and which one is south? It means we need to know the field direction. So your first finger is we don't know in which direction, but anyhow you stretch out your thumb as was shown in the previous slides. Okay, then you point your second finger towards you, out of the paper, because current is dot here. Dot means out of the paper. So current direction is shown to you, so that should be towards you, and thumb upwards. So when this is done, your first finger automatically goes from this to this, means towards right. Okay, so north and south. Now the last question of this page. Here there is a coil now. You see two marks. So it means one side has current outward and the other side has current inward. Means it may be a coil which is placed horizontally, current, and this is a rectangular coil, and current is entering this way, going this way, and coming out of the coil towards you. Okay, so this is the direction. So, okay, coil is placed horizontally and it is entering, current is entering. So what is the direction of force on this cross side? So apply Fleming's left hand rule. Field from north to south, current into, so your first finger should point towards your right side and your second finger should point towards the laptop screen, thumb comes downwards. Okay, so this side experiences force in the downward direction. And what about this one? Because the current direction is opposite, means it will be experiencing force in upward direction. We can check also. Field same direction, north to south, and current outward, so force is upward. So this side experiences force up and this side experiences force down. Okay, so it means this will tend to rotate the coil, and this is what we will apply for DC motor. Okay, so the direction of force will in the two sides of the coil are opposite, but the turning effect is produced because both the forces will tend to rotate this in one direction. What is that direction? That is clockwise. Okay, so that will rotate. So this is electric motor, DC motor, and this is placed between the, this is a rectangular coil I wanted to show. Okay, the current entering from this side, arrow shows current entering. It means if I show this coil by diagram, I will put cross here for this side and dot here for this side because current outward. Okay, so here force upwards and this side is experiencing force in the downward direction. Okay, and rest of the part of the DC motor, electric motor, these things we will study later. Here only I am talking about the coil. The coil will experience force in such a way that will produce clockwise rotation. That is, this side will experience force downwards and this side will experience force upwards. So both the forces will be producing the turning effect in one direction. So this, again we can have a look at this. Okay, this one we already filled in, and the force direction current into, so current into field in the opposite from north to south, so force is downwards. Here force is given. What is the direction of current with this magnetic field from north to south? If you apply the rule, that is keep your fingers, so current, your second finger automatically comes out, okay, towards you. Here the poles are to be marked, current direction is known and the force is known, and we already did it. And the main thing of repeating this slide is what? To show you that motor effect, this turning effect. Okay, that coil which was having current in this way, current out. Okay, so that coil experiences force and it rotates. Okay, then about the DC motor we will study in the next video. Allah